is Polyhedral Gauss sums and polytopes is
Thank you. Thank you thanks to the organizers for doing a great job. It's almost humanly possible. So this came out of some other work. It's continuing work, but let me start. By the way, this is joint with Romanos Malikiotis, who was my postdoc in Singapore, and Jian Yi, who was my undergraduate student in Singapore. Romanos is now in Berlin, and Yi is still in Singapore. I like to think about discrete volumes of objects, and there are many ways to discretize volume. And one nice way is to attach a small sphere to center a sphere at, let's say you're given some lattice, and let's say any full round lattice in Euclidean space, you center a sphere at the lattice point, and you look at the proportion of the sphere that intersects a polytope. So given a polytope, you want to discretize the volume. So you center a sphere of radius r at x. Let's say r is very, very small, so you localize the geometry. And the proportion is called the solid angle at x. And this is a local object, and then you move the sphere around and you sum all these proportions. And if r is small enough, then when a sphere is centered at a point inside the polytope, you get 1. The proportion is 1. Outside it's 0, and on the boundary it's some fraction between 0 and 1. So you get some interesting discrete volume. And we want to, so it's a lot of people study these things, McMullen and going back, Gerhardt as well, but back even further, I think. But in any case, we want to extend Gauss sums. So I'll give you the definition of the extension, and then I'll take a break into some history of, we don't have much time, but some development of tilings, because this has to do with tilings when you extend it, it turns out. So the extension of, so here's the solid angle we just talked about. You put a small sphere centered at x at a dilated version of t, so you dilate by n, and here is an integer. And this measures, again, this is just a local solid angle at x. And let's say x belongs to the lattice, integer lattice. And this is the usual quadratic exponential, so here it is. So this is an extension of a quadratic Gauss sum. So everything in the sock would be quadratic Gauss sums, and I know it's very interesting to look at non-quadratic Gauss sums, but we used it in the proofs, we used the properties of quadratic Gauss sums. So this is an extension of the Gauss sum to a polytope, a dilated polytope, and then you wonder, one natural question is, when does it collapse to mimic the closed form that Gauss had for the one-dimensional case? So in the one-dimensional case, Gauss defined this, and I guess in his memoirs, I think he said it took him 4 years to find a proof of the closed form. So so when p is the unit interval, when you dilate p by n, you get this. So in the case of a one-dimensional unit interval, and then you get, this becomes the polyhedral Gauss sum, becomes the classical Gauss sum, and then you can extend it to any polytope. Extensions were studied before, by the way, for parallelepipeds. So if p is an integer parallelepiped, you can recognize as a fundamental domain of it's a torus, right? So it's a fundamental domain for some lattice, and so it's a finite abelian group. So Gauss sums over finite abelian groups have been studied, and by Drive and other people. But here, we want to extend it beyond fundamental domains of lattices, beyond parallelepipeds to arbitrary integer polyhedra. And so here's, just to recall quickly, the closed form of Gauss. So Gauss found this closed form, as we all know, and it's natural to ask what geometric properties the integer polytope P must possess, so that now the higher dimensional Gauss sum will also have a closed form. Okay, so we want to hunt for closed forms. So we want to mimic this closed form, oops. And hunt for the geometric properties that will ensure these closed forms in higher dimensions as a first step to studying these things. So let's take a background on some tiling. So first we need to know a little bit about tiling and multi-tiling, because this will turn out to enter into the picture naturally. So So if you take an integer, this integer octagon, and move it around and translate it by integer vectors, it turns out that if you translate it by all the integer vectors, every point in the Euclidean plane will be covered exactly the same number of times. And so this is called a multi-tiler. It will multi-tile. The number of times here will be 7. And you can see this two-tiler belongs to exactly 7 copies. Oops. 1, 2, 3, 4, 5, 6, 7. And so if you keep going, every point will be covered exactly 7 times, except of course the boundary or translates around. So that's a multi-tiling. We'll go back to it. Here, for example, is a multi-tiler where it's just one tile. So we'll say it's having one tile if it just classically tiles by translations. And that's a polyhedral. I couldn't resist the Hirschhorn tiling. Hirschhorn. So Michael Hirschhorn.
Tell them about it.
What's that?
I'll tell them.
He came up with this. There's some new research actually on these Hirschhorn tilings and other tilings if you allow rotations. We will, in a second, allow reflections as well, but not arbitrary rotations. These are kind of fancier rotations. So that's what happens. You can get weird things when you allow arbitrary rotation. And a naturalization of classical tiling, a natural extension is to, instead of this being 1, you let it be k. In other words, you fix some discrete set of translations lambda. Lambda doesn't even have to be a lattice. Any discrete set, as long as there's no accumulation point of lambda here. And this says that some translation of p hits v exactly k times. So I mean there are k translations of p that hit v. Right, so every point v in space is hit exactly k times by some translation of p. And so this is the definition of multi-tiling. Every point gets covered exactly k times. And just classically, quickly, there's Minkowski-Van-Kamp-McMullen condition. It's a beautifully familiar condition. This spans about 100 years, beginning with Minkowski, or 80 years or so, beginning with Minkowski and Van-Kamp. And it says that if you're tiling by translations only, then the object must be, first it must be a polytope, secondly it must be essentially symmetric. All its facets must be essentially symmetric as well. And there's something called a Veld condition, which basically you have a codimension to flat, and you project the object in the codimension to flat, and the projection must be a square or hexagon. Okay, so we have an extension of this from 2012. Well, this is with different co-authors, Nick Ravin and Dimitri Shuriat. So with this extension, so this is what happens when you allow the object to be a multi-tiler, and I think it's very beautiful to study multi-tiles because, for example, in any fixed dimension D, it's easy to show there are finitely many of these objects. But in any fixed dimension D, there's infinitely many of these objects. So there are finitely many tilers, but infinitely many multi-tilers. In fact, a continuum, many multi-tilers in any fixed dimension. So it's a very rich collection. It allows you to do more things. Okay. So
the null conditions for tiling?
The null conditions for tiling, and yes, so it's good that you noticed, we don't know the analog yet for multi-tiling. So this is if and only if, and so far these are only, we're only able to retrieve the necessary condition. By the way, the statements are similar, the proofs are absolutely, completely different. Unfortunately, it's a lot harder, but the statement turns out to be the same as the classical Minkowski. These two conditions were given by Minkowski, and the third one was finally discovered independently by Van Kamp and McMullen. Okay, so then another, let's see, this kind of bounces quickly. Okay, another if and only if condition for multi-tiling is, and this is more related to what we're doing now, because we want to discuss the Gauss sums, is you put the local sphere centered at any point V, and you move it around. So you have a polytope P. You want to know if it multi-tiles. You move it around by some discrete set of lambda vectors, and again, it doesn't have to be a lattice necessarily. And it turns out that for any translation of P, if you look at all the lambda vectors that sit inside the translated polytope, you get exactly K for all K. So So it's a very interesting thing. It turns out, by the way, that K must be the volume. If lambda is the integer lattice, for example, or any unimodular lattice, K turns out to be the volume of the object. So it's a very interesting thing because so philosophically, this is a discrete object and this is a continuous one, the volume. So again, your approximation turns out to be exactly on the nose, the volume. So if your approximation is precise, it turns out to be so special that there's some hidden group action lurking there, and we want to understand the group. So just because the discrete volume equals a continuous volume doesn't mean that it's not obvious that there will be a group action, but it turns out that indeed there's some group. And in fact, we want to show that P will be a fundamental domain of some group action. Okay, so this gives motivation to study the general question of when is the discrete volume equal to its volume? And that's sort of the motivating underlying question. And for example, if P is an integer zonotope, if you know what a zonotope is, it's just the projection of a d-dimensional cube to a lower dimension, it always multitiles with the lattice, and the sum of the solid angles at the integer points in fact equals to the volume. So this is a nice example, and integer zonotopes are very rich. It's a nice infinite class of examples for which this holds, and the previous theorems hold. Okay, so here's a nice picture going back to the octagon. You translate the octagon by any translation, and it contains exactly 7. So the multiple K here equals 7. And because it contains exactly 7 points, then by this theorem before, we know that the octagon must multitile. And we already saw previously in the previous pictures it's multitile. By the way, if you insist on translating it so that the vertices lie on the lattice, it's still 7, even though it doesn't look like it, because the fractional solid angles, these are 3/8, and magically, if you add them up, they magically add up to 7. So it holds for every translation. Okay, here's a three-dimensional zonotope. Well, 2 flights, it doesn't matter. It's a three-dimensional zonotope. It's a projection of some 9-dimensional cube, and it does in one-tile 3 space. There are only 5 solids at 1-tile 3 space, given by the crystallographer Fedorov from 1890. So in 3 dimensions, there are only 5 such solids at tile. So here it's a zonotope, and but it does indeed multitile, as do all integer zonotopes in 3 dimensions. They do multitile. Okay, so what we'd like to do is extend the group of translations that we studied so far to a non-Euclidean group, file group, or including rotations. So let's consider the file group generated by the finite, by all the reflections about the coordinate planes. So just the simplest vanilla type file group. Its order is due to the dd factorial. I think the period and all this stuff. And we're going to work with sets that multitile the space under the action of this group G. So we want to extend the group from translations to include reflections and ask now what multitiles. But that's a fairly difficult question. So we're going to use the Gauss sums and see when the Gauss sums allow complete truncation. In other words, when do they truncate to exactly the volume times something in 1 dimension. And so, oh, by the way, there is, the whole thing that makes everything work is sort of this, that there's still a fundamental domain. So everything that makes things work is there's some fundamental domain. In this case, it's not a abelian, but it's still a fundamental domain for the group action. And here's one fundamental domain for this group. It's this particular simplex. And this simplex in 3 dimensions, we'll look at the simplex in 3 dimensions in a bit. And so this makes a lot of things work. There are many fundamental domains, but we'll look at this one. Okay, so here's the first theorem with Romanos and Yishi. Actually, it should be the last name, Jan Yishi. If P multitiles the space with the group G, this file group, then indeed you get the closed form analog of Gauss. So indeed everything collapses, and the polyhedral Gauss sum becomes just a volume times the G of n was the 1-dimensional Gauss sum. Now you raise it to the d power, and so indeed you get the closed form. And so the proof of this is well, it's not too bad, but we don't have enough time to go into the proofs. So you wonder, okay, that's nice. If it multi-tiles, this is true. What about the converse? We don't have tools yet, so we have one partial converse in 3 dimensions. In other words, if this closed form holds, does the object tile or multi-tile space? And that's a very, very difficult question, and I'd love to see more tools, but we just brute forced in 3 dimensions. We said, okay, so let's look at the fundamental. This is the fundamental domain for this vial group, and if you have a lattice attribution of volume 1/6 such that it has the Gauss sum closed form, doesn't necessarily have to be a fundamental domain or an image of the fundamental domain. And so it turns out it does, but this took about almost 20 pages of hard computation. So we don't have really the right tools, I think. So it's funny, I don't know if this looks hard or not, but this turned out to be extremely hard, and this turned out to be fairly straightforward. Well, because here you already have the group in your hand, and here you're hunting for the group. And so we conjecture that whenever the polyhedral Gauss sum does collapse to a closed form, in fact, there will be a group action. And P will be somehow, well, anyway, it will multi-tile the space with the group G under this. Well, I should say that if P is an integer, let's say an integer polytope, the vertices are integers, in this context, if you have a closed form for the Gauss sum, then we conjecture this happens. But again, I'll be honest, this took a lot of brute force and a lot of algebraic number theory too. So we worked in some extension field of degree 6, or no, 8, I think, and did some algebraic number theory. But there should be some easier methods. So if you know of any methods, I'd love to see these things. So we're going forward and extending the groups. Okay, happy birthday, Christian.
Are there any questions for?
Can you go back, I think it's like halfway through.
To what?
I'm forgetting, but I'll see it. Oh. Oops. A little too far.
It's too far.
I think it was after the after this. Oh yeah, it was this. So sorry, I'm trying to remember what I was going to ask, but you're saying if this is constant, if it's this constant k, then it will multi-tile. So
as long as you translate by all translation.
Yeah, sorry, I'm forgetting what I thought I was going to ask.
If you remember, let me know.
Yeah. Oh, I know what it was. I was confused about what the V was, but now it makes sense. Now that I didn't see the V and RD. Yeah.
Okay.
You think if a polytope multi-tiles with K things, that it can be decomposed into a union of K zonotopes?
No, because I think it's if you look at the dimension 4, so if you look at the Voronoi cells, so in dimension 4, there's a 24 cell, which is the Voronoi cell of the D4 lattice. That does multi-tile tile, and I do not think it's a union of zonotope.
Are there any other questions? If not, let's thank us.